Good day, my people. Good day, um, my fellow classmates. You are welcome to another session in Chemistry 235. That's basic organic chemistry, where we learn the rudiment of organic chemistry. Today, we shall be discussing factors affecting structure and physical properties of organic compounds. In our last lesson, we discussed the electron theory in organic chemistry, where we talk about the arrangement of electron in an atom and the way electrons are distributed in a given atom. We also mentioned the electronic configuration of an atom in the ground state. And we briefly mentioned if an electron gain energy, it can be excited and you have an excited state. Today, we want to discuss factors affecting structure and physical properties of organic compounds. At the end of today's lecture, at the end of this lesson, we should be able to identify intermolecular forces. We should be able to identify physical properties of organic compounds, and we should be able to discuss the physical properties, various physical properties of organic compounds, as well as discuss how these properties, how intermolecular forces affect these properties. Intermolecular forces are forces that act between molecules. The type of intermolecular forces that occur in a substance will affect its physical properties, such as the phase, the melting point, and the boiling point. Recall that phase of a substance is determined by how strong the forces are between its particles. The weaker the forces, the more likely that the substance are to exist as a gas. And if the forces are very strong, the particles are held closely together in a solid structure. Also, the temperature of a material affects the energy of its particles. The more energy the particles have, the more likely they are to be able to overcome the forces that are holding them together. This can cause a change in the phase. For instance, if you take water for example, it exists in three phases. You have ice, that is the solid state of water. Then you have the liquid, when the water is in liquid case, and you have the gas, and that is water vapor. Forces between molecules that bind them together are known as intermolecular forces. Intermolecular forces allow us to determine which substances are likely to dissolve in other substance and what the melting and boiling point of substances are. Without intermolecular forces holding molecules together, we will not exist. Remember that okay, let us now discuss different type of intermolecular forces. To understand these intermolecular forces, you need to remember the concept of dipole in a molecule. That is when the charges in the molecule are unevenly charged. As you can see here, you have positive and negative end. In each one end is positive, the other end is negative. Now, these are some of the intermolecular forces. Dipole forces. When one dipole molecule comes into contact with another dipole molecule, the positive pole of one molecule will be attracted to the negative pole of the other, and the molecule will be held together in this way. You also have dipole moment. It's one of the intermolecular forces. Dipole moment of a bond is equal to the magnitude of the charge on one of the bonded atoms times the distance between the bonded atom. That is, for instance, in this case, you have the positive end, negative end. The magnitude of this charge multiplied by this distance is equal to dipole moment. And here we have a list of some compounds and their dipole moment. The unit of dipole moment is dpi. For methanol, for example, the bond between carbon and oxygen has a dipole moment of 0.7 dpi. In iodomethane, the bond between iodine and carbon has a dipole moment of 1.2, and so on, as you have it here. Molecules with dipole moment are attracted to one another because they can align themselves in such a way that the positive end of one dipole is adjacent to the negative end of another dipole. These electrostatic attractive forces are called dipole interaction. We also have van der Waals, though not as strong as covalent bond. Van der Waals forces. For van der Waals forces, there are two types. One is induced dipole forces. We have dipole-induced dipole intermolecular forces, which are also known as London forces or dispersion forces. And this is as a result of the fact that as electron is revolving around the atom, there will be a time in which the negative electron will be concentrated on one end of the atom. That end will become temporarily and partially negative. And this end that is negative will now attract the positive end of another atom, and there will be an attraction between the opposite charges, a temporary attraction which does not last long. This type of attraction is what is termed induced dipole forces or London forces. As you can see here, this is the normal atom. Then as the atom electron is moving around, at a point in time when it's concentrated at one end, it's attracted to the positive of another atom, and there's a temporary attraction between the two atoms. Then you have dipole-induced dipole forces. These forces exist between dipoles and non-polar molecules. The dipole, you have a dipole molecule and a non-polar molecule. The dipole will induce polarity in the non-polar molecule and thus creating an attraction between the two. Then hydrogen bond is another one. Hydrogen bond is a type of molecular bond that involves hydrogen atom. When a molecule contains a hydrogen atom which is covalently bonded to a small highly electronegative atom, oxygen, nitrogen, or fluorine, this type of intermolecular force can occur. The highly electronegative atom on one molecule will attract the hydrogen atom on another molecule, as you can see in this molecule here, ethanol. In ethanol, hydrogen is bonded to oxygen. So the hydrogen of one molecule is attracted to the oxygen of another molecule. The attraction between them is what is termed as hydrogen bonding. Then another factor that affects physical property is the molecular shape of the atom. Depending on how the lattices are arranged, whether they are rigid, compact, or symmetrical, they will determine whether the molecule will be fit, compact, and packed together, as you have in this case, as solid, or may not be. In some cases, the molecule may not be able to come together as we have it here. So the shape of a molecule also affects the physical property. An example is butanol, and it is depicted in these four examples of butanol. We have the normal butanol, the straight chain butanol, isobutanol, also known as secondary butanol. Then you have isobutanol or 2-methyl propanol. Then you have the tertiary butanol, which is 2-methyl propanol. If you look at the four, they all have the same molecular formula, but the shape are different. This will also affect the way the molecules interact with each other. As you can see in this table, these are the four different butanol, which having the same molecular formula, only the structures are different. You can see in their density, the boiling point are different, the melting points are also different. Whereas tertiary butanol boils at 83 degrees, secondary butanol boils at 100 degrees Celsius, while isobutanol boils at 108, and normal butanol boils at 117. This is because in normal butanol, it's a straight chain alkane. The molecules are able to align together perfectly. Thus, to break them apart, you need more energy. That's why it has the highest boiling point. Similarly, if you look at tertiary butanol, it's like it has a zigzag shape. The shape cannot be fitted perfectly. Thus, it has the lowest boiling point, and as you have it all along. Another example of a compound which is affected by the molecular shape is the fatty acids, the saturated fatty acid and unsaturated fatty acid. And the typical example here is oleic acid and stearic acid. Oleic acid is unsaturated. You can see from the structure. Compare with stearic acid. They have the same molecular formula, the same number of atoms, the same number of carbon atom, same number of hydrogen, same number of oxygen. But because of the unsaturation, oleic acid is not straight. It's like a zigzag molecule, whereas stearic is a straight. Stearic acid is able to arrange themselves together and fix together perfectly. Okay, and that's why it has a higher melting point of 70 degrees, while stearic oleic acid has a melting point of 16 degrees, which is much lower than that of stearic. In fact, stearic acid is solid at room temperature, while oleic acid is oil. This oil, our normal oil, at room temperature. Now, physical properties for organic compounds. One of them is the viscosity. Viscosity is a measure of how much a liquid resists flowing. Okay, how much a liquid resists flowing, how easy for a liquid to flow or to pour away. That is viscosity. The higher the viscosity, the more viscous substance is. Viscosity is also the resistance to flow of a liquid. For instance, if you consider water and honey, you can see that when you are pouring hot water and honey in a cup, water will pour faster than honey, meaning that the honey is more viscous than water. Another illustration is this. If you have two different liquids in a jar, for example, if you fill two jars, one with glycerol and the other with water, and throw in a ball into the two jars and monitor how fast the ball fall into the bottom of the jar. That will tell you how viscous a liquid is. Substances with stronger intermolecular forces are more viscous than substances with weaker intermolecular forces. The stronger the intermolecular forces, the more the substance will resist flowing. The greater the internal friction, the more a substance will slow down an object moving through it. Okay. Then another property is density, physical property. Density is a measure of the mass per unit volume, as depicted in this equation: mass per unit, mass over volume. In most cases, the solid substances are more dense. They are more dense, except ice, which is less dense than the liquid water. Okay, this phenomenon can be explained by the strong intermolecular forces found in a solid. The forces pull together the molecules together, which result in more molecules in 1 unit per volume, in 1 unit of volume than in the liquid or gas phases. The more molecules in the unit volume, the denser and heavier that molecule of the substance. Density can be used to separate different liquids. The more dense liquid setting will settle at the bottom of the container, while the less dense will float on top. Similarly, if you throw a leaf into a river or pond, the leaf will float because the leaf is less dense than water. But if you throw a rock, the rock will sink into the river or pond because rock is more dense. This is due to the different density of the two substances. Rocks are more dense than water, while leaves are less dense than water. This is a typical example to illustrate density of substances. The right hand side here in this cylinder are different liquid in the same container. You can see that the liquid are separated according to their density. The one that is more dense is at the top, and so on and so forth. Also, if you throw three different types of objects in a liquid of water, the object will behave according to the density. The one that is flowing on top of the water is the less dense. The one that say, I mean, that sink but did not go to the bottom is more dense than this one, but less dense than this other one that all sink into the bottom of the jar. Then you talk about melting and boiling point. These are other physical properties. Intermolecular forces affect the boiling and melting point of the substances. Substances with weak intermolecular forces will have low melting and boiling point, as less energy heat is needed to overcome these forces. Okay, substances with weak intermolecular forces will have low melting point and boiling point. Those with strong intermolecular forces will have high melting point and high boiling point because you will need more energy to overcome the forces of attraction. When the temperature of a substance is raised beyond its melting or boiling point, the intermolecular forces are not weakened, only that the molecules attain more energy to overcome the forces. Rather, the molecule have enough energy to overcome those forces. This table also shows the melting point and boiling point of different uh, substances from ethane to ethanoic acid. If you look at ethane, the intermolecular forces operating in ethane, being an hydrocarbon, is induced dipole, and the melting point is minus 183, the boiling point is minus 89, and it exists as gas. In fact, the first three, ethane, dimethyl ether, chloroethane, ordinarily exist as gas because they have weak intermolecular forces. But if you go to pentane, propanol, ethanol, butanol, they are liquid. Even ethanoic acid are also liquid. But as you go down, the intermolecular forces, the strength in the intermolecular forces increases, thus the melting point and the boiling point also increases as you go down the table. Flammability is another property. Flammability Flammability is a measure of how easy it will be for a substance to catch alight and burn. In other words, it is the heat with which a metal is ignited, the intensity with which it burns and release heat once ignited. That is flammability. Then there's another phenomenon, flash point, which you need to know. Flash point of a substance is the lowest temperature that is likely to form a gaseous mixture you could set alight. Note the difference between flash point and flammability. Flash point is talking about temperature, the temperature at which it forms gaseous and can be ignited, while flammability is a measure of how substances can be ignited. If a liquid has a low enough flash point, it is considered to be flammable. Those with higher flash point are considered to be non-flammable. A substance that is classified as non-flammable can still be forced to burn, but it will not burn easily. It will not ignite easily. Vapor pressure is another related property. It's also related to flammability. The pressure exerted at a specific temperature on a solid or liquid compound by a molecule of that compound that are in the gas phase. This what happened here is that if you have a liquid substance, not all the molecules of that liquid are in liquid state. Some of the molecules are in the gaseous state. The are over the liquid substances. Now, the pressure exerted by those molecules in the gaseous state is what is referred to as vapor pressure. These molecules have enough energy to overcome the intermolecular forces, holding the majority of the substances in the liquid or solid phase together. That is why they exist as gas. This gas molecule exert pressure on the liquid or solid and the container. That pressure is what is referred to as vapor pressure of that substance. The weaker the intermolecular forces within a substance, the higher the vapor pressure. And compounds with higher vapor pressures have lower flash point and are therefore more flammable. So you can see where vapor pressure flash point and flammability comes together. When a compound has higher vapor pressures, it has lower flash point, and therefore it's a flammable substance. The illustrative vapor pressure with this chart here. Here we have three different substances: water, ethanol, propanol. Because in water, intermolecular forces is strong, so less substances of molecule of water are in the gaseous phase, so the vapor pressure is low. Take ethanol. Here it has a weaker intermolecular forces than water, so it has more molecule in the gaseous phase and it has higher vapor pressure. And propanol has higher vapor pressure than ethanol, and this is how the vapor pressure increases. Water with lowest, propanone with the highest vapor pressure. You can also look at the boiling point of the three, compare the boiling point of the three substances. While propanol boils at 56 degrees, ethanol boils at 78, and water boils at 100. Also, this table shows the different vapor pressure, flash point, and flammability of different substances from ethane to water. And you can see that as the intermolecular forces, the strength increases as the strength of intermolecular forces increases as you go down the table. Okay, the vapor pressure decreases and the flash point also increases. Okay, solubility. Solubility is another physical property that's related to the intermolecular forces. And solubility is a measure of the ability of a substance to dissolve in another substance. The amount of the substance that can dissolve is the measure of its solubility. In most cases, hydroxy group makes alcohol more molecule polar and therefore more likely to be soluble in water. But the carbon chain resists solubility. So there are two opposing trends in the alcohols. You have the hydroxy group, you have the carbon chain. So it now goes that the alcohols with shorter chains, with shorter carbon chains, are usually more soluble in water than those with longer carbon chains. In fact, the higher the number of carbon atoms, the lower the solubility. Alcohols also have higher boiling point than hydrocarbon because of the strong hydrogen bond between hydrogen atoms of one hydroxy group and the oxygen atom of another hydroxy group. You can see that in alcohol, apart from the dipole attractive forces that is operating, you also have hydrogen bonding. So alcohols have higher boiling point than usual hydrocarbon. We can also visualize solubility in this chart here. If you look at the first test tube on the left, this is a perfectly soluble substances in the solvent. You can see that in this substance, only apart from the color, you can't see any particle. But if you consider the second one, you can see some particle suspended in the liquid. That's why you have suspension. And you have some particles at the bottom. We call it precipitate. You can see this one is sparingly soluble. This one is sparingly soluble. But if you look at the third one, all the substance settle at the bottom. This one is non-soluble. We describe this as being non-soluble. For today, in summary, we have been able to identify that intermolecular forces, that is the dipole moment. We have discussed dipole moment as intermolecular forces, van der Waals forces, hydrogen bonding, shape of molecules. There are factors affecting physical properties such as density, viscosity, boiling point, melting point, flammability, vapor pressure, solubility of organic compounds. Subsequently, we shall go further to discuss various classes of organic compounds and how these intermolecular forces affect their property. In the next lesson that will be discussed, we discuss particularly homologous series and how the intermolecular forces affect the properties of these compounds. Before we go in this class, I want you to take this as an homework. Let me say homework for you. You have this question here. You have this table here. We are given propane. It has a melting point of minus 188, boiling point of minus 42. Butanoic acid minus 77.9, 163.5 boiling point. Bromoethane minus 118, 38.5 boiling point. And diethyl ether, it has a melting point of minus 116.3 and boiling point of 34.6. Now use the information you have in this table to complete the table below. This is an exercise for you. Also, here is another one. This one states which container, this one or this one, has the compound with higher vapor pressure. Explain your answer. Then you have this one. Draw the condensed structural formula for each of propanoic acid and butanol. Propanoic acid has a vapor pressure of 0.32 kilopascal at 20 degrees Celsius, and butanol has a vapor pressure of 0.64 kilopascal at 20 degrees Celsius. Explain the difference in the vapor pressure. This, you can use this as your further readings while we see you in next class. Thank you for your reading and God bless. See you